Hey everyone, and welcome back for another deep dive. Today we are going deep into the world of robots, but not just any robots. We're talking about robots that are being designed to sense and react more like living beings.
It's pretty incredible stuff.
It is, it is. And to help us break it all down, we've got a fascinating paper here from some of the top researchers in the field.
Yeah, some real pioneers.
And we are going to be talking all about embodied neuromorphic intelligence.
That's a mouthful.
It is a mouthful. But once we break it down, it's going to be really fascinating to see just how much this is going to change how robots are going to be integrated into our world. So get ready for some seriously cool insights into how these robots are being designed to kind of like see and respond to the world around them, all thanks to inspiration from the human brain.
You know, the human brain has had a few billion years to evolve.
That's right.
And we're just starting to tap into some of those secrets to really build some pretty amazing technology. The big idea here is to create robots that can move beyond just operating in our world, but truly understanding and interacting with it in a much more nuanced way.
Okay, so first things first, for those of us who don't spend our days building robots, what exactly does embodied neuromorphic intelligence even mean?
Yeah, it is a mouthful. Essentially, it's about building robots that don't just think like humans, but actually process information and respond to the world in ways that are much closer to how living organisms do.
Like a dog or a cat?
Yeah, exactly. It's not just about the brain. It's about connecting that processing power to the robot's body and allowing it to sense, react, and adapt in a physically grounded way.
So it's less about a robot going through a checklist of instructions and more about it instantly reacting to what's happening around it.
Exactly. The paper actually uses a great example to illustrate this. Imagine a robot trying to navigate a crowded room while also holding a delicate object. A traditional robot would struggle to balance the complex task of long-term path planning with the need to constantly adjust its grip based on tiny changes in pressure or texture, it's feeling through its hand.
Right.
Humans, we do this kind of thing all the time without even thinking about it. But for robots, it's been a massive computational challenge.
That's a really great point because it's like we take for granted how much we're constantly processing and reacting to without even realizing it.
Right.
But this is where the whole neuromorphic part comes in, right? What exactly makes this approach different?
The key here is that instead of trying to program every possible scenario into a robot's software, researchers are trying to design systems that mimic the structure and function of the human brain. And this field is called neuromorphic engineering, and it's leading to some incredibly innovative ways of building robot brains.
So it's about taking cues from nature to build better robots.
Exactly.
That makes sense, but I'm curious, how does this play out in the real world? How do you build a robot that sees the world more like we do?
Well, think about how a traditional camera works. It captures a series of still images or snapshots at regular intervals.
Right.
Now imagine a robot trying to catch a ball using only that type of vision. It would miss a lot of information between those snapshots.
Right.
But in the real world, we don't see in stills, we see continuous movement. That's where event-driven vision sensors come in.
Okay.
Instead of capturing whole images, these sensors only react to changes in light intensity, kind of like how our own eyes are most sensitive to movement.
So instead of taking pictures, these sensors are recording a kind of constant video feed of what's changing in the robot's field of vision.
That's a great way to put it.
That seems like it would generate a ton of data. What do they do with all that information?
That's where it gets even more interesting. The paper explains how researchers are developing something called computational primitives. Think of these like building blocks inspired by neural circuits in the brain, each designed to handle a specific task. For example, one primitive might be specialized for recognizing the edges of objects, while another is focused on detecting motion.
So each primitive is like a little mini program. And by combining them, the robot can build up more complex behaviors.
Exactly. It's kind of like having a dictionary of these mini programs, and the robot can select and combine them as needed to make sense of the constant stream of information from its sensors.
That's so cool. So these robots are getting a much richer, more dynamic view of the world. But what about the other senses? Are researchers working on building neuromorphic hearing or touch?
They absolutely are. While vision has been a major focus, there's a growing movement to develop neuromorphic sensors for touch, hearing, and even senses that humans don't have. Imagine robots that can feel subtle changes in texture, hear frequencies we can't, or even detect things like changes in air pressure or magnetic fields.
Whoa. if they can combine all of that information we're talking about robots with a level of awareness that goes way beyond anything we've ever seen before.
It's really pushing the boundaries.
This is really incredible stuff. But surely there must be some hurdles to making all of this a reality. What are some of the biggest challenges researchers are facing in this field?
You're right, there are definitely some challenges to tackle. The paper highlights a few key ones. Firstly, the tools and methods for developing and programming these neuromorphic systems are still very specialized. Not many researchers have the expertise to work with them effectively.
So it's like having all the parts to build a spaceship, but only a few people know how to read the instructions.
Yeah, that's a great analogy. Another big challenge is figuring out how to integrate all of these different sensing and processing components in a way that truly mimics the seamless, adaptive nature of biological systems. We can build a robot that sees and feels, but getting those senses to work together as well as they do in a human is a whole other level of complexity.
It sounds like there's a lot of ground to cover, but the potential here is really mind-blowing. I'm definitely going to need some time to process all of this.
It is. We're really just scratching the surface here,
But it's exciting.
Oh, it is. It's absolutely fascinating.
Well, I, for one, am excited to see where this all leads. But before we get too far ahead of ourselves, let's shift gears for a moment and talk about some of the practical applications of this technology. What are some of the specific things these robots could do that current robots can't?
That's a great question, and one that researchers are actively exploring. Let's take a closer look at some of those potential applications after a quick break. We'll be right back.
All right, we're back and ready to really kind of like dive into the real-world potential of these amazing robots. So where are we going to see this? Where could this really make a difference?
I think healthcare is going to be one of the areas where this technology could be truly transformative.
Yeah, how so?
Well, imagine you've got a surgeon, and they're operating, and they've got this robot assisting them. And this robot can not only see with incredible precision, much better than the human eye, but also it can feel those subtle differences in tissue density.
Oh, wow.
And all while adapting to, unexpected situations in real time.
So it's almost like an extension of the surgeon's own senses.
That's a great way to put it, yeah. It's not just about robots doing things for us, but actually working with us in a much more, integrated way.
But what about outside of the operating room? Are there other areas of healthcare where this type of robot could make a difference?
Oh, absolutely. I mean, think about elder care. You could have a robot that's providing assistance with daily tasks, things that are, maybe difficult for an older person to do.
Right.
But because it has this delicate sense of touch and the ability to process social cues, it can offer a level of companionship as well, something that goes beyond what current robots can do.
That's such an important point, that it's not just about the physical tasks, it's about that emotional connection as well.
Yeah.
It seems like, when we talk about robots, we often focus on like the physical capabilities, but the ability to actually understand and respond to human needs on that emotional level, that's a whole other dimension, isn't it?
It really is.
But let's shift gears for a moment and talk about some of the technical details. Because, obviously, we don't want to get too bogged down in the weeds here, but the paper does mention some pretty complex concepts like dynamic neural fields and neural state machines.
Right.
Can you break those down for us in a way that's easy to understand?
Sure. Let's start with dynamic neural fields, or DNFs for short. Imagine you walk into a room, right,
Yeah.
and you immediately recognize a chair, even if it's partially hidden behind a table. Your brain's doing this amazing thing where it's constantly building and updating a kind of mental map of the room,
Right.
filling in the missing pieces based on what you've seen before. And DNFs work in a similar way, allowing a robot to create this kind of dynamic representation of its environment that changes in real time based on the information it's receiving from its sensors.
So it's almost like the robot is constantly making predictions about what's around it, even if it can't see everything directly.
Exactly.
Yeah.
Yeah. And that's where neural state machines, or NSMs, come in. Think about how you might change your behavior depending on the situation you're in.
Okay.
Like if you're at a party, you might be more outgoing and talkative.
Right.
Whereas at a library, you'd be quieter and more focused.
Right.
NSMs allow robots to switch between different modes in a similar way,
Right.
adapting their actions and responses based on the context they're in. So it's like giving the robot different personalities almost.
Almost like giving them different personalities or different modes that they can kind of like switch between depending on what's happening around them. It's starting to sound like we're talking about robots that can actually think for themselves.
In a way, yes. But it's important to remember that these robots are still being designed and programmed by humans.
Right.
We're giving them the tools to learn and adapt, but we're also setting the boundaries for how they do that. We're not just setting them loose.
Right, we're not just creating like Frankenstein's monster and letting it run wild. But, that does bring up an important question, which is the question of safety. Because I think a lot of people, when they hear about, artificial intelligence and robots becoming more intelligent, there's this fear of, like, what happens when they become too intelligent?
Right.
How do we make sure that these robots are safe, that they don't pose a threat to humans?
Absolutely. That's a crucial question. And it's one that researchers are very much aware of. And I think one of the things that makes embodied neuromorphic intelligence so exciting is that it is grounded in the real world. These robots aren't just theoretical constructs. They have physical bodies. They have limitations.
So unlike those sci-fi movies where the robots develop superintelligence and decide to, like, take over the world.
All right. Exactly.
These robots are a little bit more constrained by their physical form and their dependence on real-world interactions.
Exactly. And, the way these robots learn and adapt is heavily influenced by their interactions with humans. We can design them to be inherently cooperative, to prioritize human safety. It's like teaching a child. You teach them right from wrong.
So we're almost shaping their brains, so to speak, through our interactions with them, just like we would with any intelligent being.
Yeah, that's a great way to think about it.
So it sounds like we're a long way off from those dystopian robot takeover scenarios.
I would say so, yeah. The focus of this research is on building robots that can augment human capabilities, not replace them entirely. It's about creating a future where humans and robots can coexist and work together to solve some of the world's biggest challenges.
I like the sound of that. But let's be realistic for a moment. How long before we actually see these amazing robots out in the real world, doing these things? Are we talking 5 years, 10 years, 50 years?
It's always hard to give an exact timeline.
Of course.
But progress is happening rapidly. The paper mentions some really exciting developments like the use of neuromorphic chips to control robots in real time.
Okay.
They're also making significant strides in developing new algorithms and software tools that make it easier to work with these complex systems. So it's moving quickly.
So while we might not have robot butlers serving us breakfast just yet,
Not quite yet.
the building blocks are definitely being put in place. This research is really kind of pushing the boundaries of what we thought was possible with robotics. I'm really eager to see what the future holds. What about you?
Absolutely. It's a very exciting time to be, following this field. And I think what's really interesting is it's not just about the robots themselves. It's about this incredible collaboration that's happening between different scientific fields.
Oh, how so?
Well, to really understand embodied neuromorphic intelligence, you need expertise from robotics, obviously, but also from neuroscience, computer science, even material science.
So it's really a massive team effort. It's like a scientific, all-star team coming together to make this happen.
Exactly, yeah. And it's not always easy. I mean, these are very different fields, right?
Right.
With their own ways of thinking and doing things. And that's also what makes it so exciting.
But how does that actually work in practice? I mean, you got these, brilliant minds from all these different fields. They're all coming together.
Right.
How do they actually collaborate?
Well, for example, you've got neuroscientists. They're helping roboticists to understand how the human brain processes information.
Okay.
And that can inspire new algorithms for robot perception and control. And at the same time, the roboticists are providing real-world test beds for those algorithms.
Oh, interesting.
So it's actually helping neuroscientists refine their understanding of how the brain works. So it's really this two-way street, with each field benefiting from the other's expertise.
I love that. It's like this beautiful kind of like synergy happening between all these different fields. It's a really cool way to approach research. Are there any like specific examples of this collaboration in action?
Oh, yeah. There are teams all over the world doing incredible work in this area. For example, there's researchers at the Italian Institute of Technology. They're integrating neuromorphic vision and touch sensors into their iCub humanoid robot.
What is iCub?
So iCub is it's basically a humanoid robot.
Okay.
And they're basically giving it a brain inspired by the human brain. So it can actually walk and talk and interact with its environment. And it allows them to, take these theoretical concepts and actually put them to the test in the real world.
So it's like watching science fiction become reality right in front of our eyes.
It really is. It's amazing. And there are many other examples. You've got teams at the University of Zurich and ETH Zurich. They're developing some of the most advanced neuromorphic chips in the world, which are being used to control robots and drones with like incredible efficiency and agility.
So it's not just happening in like research labs. Are we seeing any interest from industry in this? Because obviously, industry is always looking for, ways to improve efficiency and, create new products.
Oh, absolutely. Yeah. You've got companies like Intel and IBM. They're making significant investments in neuromorphic computing. They see its potential for a wide range of applications, from self-driving cars to personalized medicine.
This is all incredibly exciting, but I have to ask, what about the potential downsides? Are there any risks or ethical concerns we should be thinking about as this technology develops?
That's a very important question. I think one of the biggest challenges is going to be making sure that as this technology develops, that we use it responsibly, that we think about how to prevent its misuse, how to protect people's privacy, and how to ensure that ultimately it's beneficial to society as a whole.
So it's not just about the technology itself, but about the ethical framework we create around it. It sounds like we need to be having some serious conversations, not just as scientists and engineers, but as a society, about how to ensure that these robots are developed and deployed responsibly.
I completely agree.
This has been an amazing conversation. It feels like we've only just scratched the surface of what's possible with embodied neuromorphic intelligence.
You really have. There's so much more to explore.
There is, and unfortunately we're out of time for today. But hey, that's the beauty of knowledge, isn't it? There's always more to discover. So to all our listeners out there, keep exploring, keep questioning, and keep diving deep into the world of knowledge. All right, we're back. And we've covered a lot of ground here talking about embodied neuromorphic intelligence. We've talked about the what, we've talked about the how, but now I kind of want to get philosophical for a minute.
Okay.
Why is this research so important in the grand scheme of things? What kind of future could this lead to?
That's a really fascinating question. I think if we kind of step back and look at the bigger picture, what's truly revolutionary about embodied neuromorphic intelligence is that it's really changing our fundamental understanding of what a robot can be. We're moving away from the idea of robots as simply, programmable machines and toward this vision of robots as almost like artificial organisms, entities that can learn, adapt, and interact with the world in a way that's much closer to how living beings do. Not just following a set of instructions.
So it's not just about building robots that are efficient or powerful. It's about building robots that can truly understand, respond to the complexity of the world around them.
Exactly. Yeah.
That seems like a huge shift in perspective. What are some of the areas where this kind of thinking could really make a difference?
I think space exploration is a really obvious one. I mean, imagine you've got a robot with embodied neuromorphic intelligence, and you send it to, explore a distant planet.
Okay, yeah.
Right. It can navigate, challenging terrain, adapt to unexpected conditions, and even make decisions autonomously based on what it's sensing in the environment. You know, you're not having to program it for every possible scenario.
It's almost like sending a robotic scientist out into the cosmos.
Exactly.
Instead of just following a set of instructions, it can actually make discoveries on its own.
Right.
And send back data that could completely reshape our understanding of the universe. But let's bring things back down to Earth for a moment.
Yeah.
What about the potential impact on our everyday lives? How could these robots change the way we live, work, interact with each other?
Well, the possibilities are really incredible. I mean, imagine, for instance, robots that can assist people with disabilities, right?
Yes.
Providing a level of personalized support that goes far beyond what's currently possible. Or robots that can work in hazardous environments, right? Protecting humans from jobs that are dangerous.
It seems like we're talking about a future where robots aren't just replacing humans, but actually augmenting human capabilities. Allowing us to do things that we never could have done before.
Exactly, yeah.
But with all this talk about the potential benefits, and I'm definitely getting excited about this, what about the potential downsides? Are there things we need to be cautious about as this technology advances?
As with any powerful technology, there's always a potential for misuse. So we need to be very thoughtful about how we design these robots, ensuring that they're aligned with our values and that they're used for good.
So it's not just about the technology itself, but about the ethical framework we create around it. It sounds like we need to be having some pretty serious conversations, not just as scientists and engineers, but as a society,
Oh,
about how to make sure that these robots are developed and deployed responsibly.
I think that's a very important point, yeah.
This has been an amazing conversation. It feels like we've only just scratched the surface of what's possible.
I completely agree.
So much more to explore. But unfortunately, that's all the time we have for today's deep dive. But hey, that's the beauty of knowledge, right? There's always more to discover. So keep exploring, keep questioning, and keep diving deep. We'll see you next time.